David Smith here with one more Flipped Classroom math video. 3 tips before we start. First, you can increase or decrease the playback speed if that helps you get through the video. Second, you can pause the video at any time to catch up with your notes. Third, you can turn on the captions to watch my words go by on the bottom of your screen. Today's lesson covers probability distributions and expected or mean value. Now what this is if you have a big old probability experiment, like you're rolling dice or you're flipping coins, you're doing a bunch of trials, what is the expected value or the mean value if you do that? So like what's the average outcome of a big probability distribution type experiment? And this one's going to be a little complicated because it's going to start off with an algebraic articulation of our probability distribution, and then we'll do our mean calculation or our expected value. So check this out. We have discrete random variable u, uppercase U, and it's defined in the following way. The probability of discrete random variable u, when we go through all the little u's, these are all the values that it can take, is going to be k. Now whenever you see k here, you're going to have to think, oh, this is something we have to figure out what it is, and that is true. We're going to find our value by taking k and multiplying it by u minus 3 times 8 minus u, and then of course they're going to give us some values that we can use for u. So u is an element of this set, 4, 5, 6, 7. So that's going to make it pretty straightforward. There's only going to be 4 values in our distribution. So first step is to create your distribution table. Okay, so I got your table started for you. We have our uppercase U, and that's representing all the values that we can put in. That's 4, 5, 6, 7. And then we have our probability of big U equaling little u, and we're going to put those values in there. So now what I want you to do, this is kind of a big critical thinking step. We did it in our last lesson. I want you to figure out what goes in each of those spots. So think real hard. Think about what you've got your values for plugging in and what your expression is there. Okay, I did the first one for you here. Here's our expression. We're going to plug in for the little u, and so I get k times 4 minus 3 times 8 minus 4, which ends up giving me 4k. I don't know exactly what the probability is yet of this variable, or of when the variable is 4, but I can say it's 4k. So now do the same thing and populate your table for 5, 6, and 7. Okay, I went ahead and did that algebra, pretty simple calculations, and I get 6k, 6k, and then back to 4k. If you're not sure how to do that, I would say pause the video and work that math. You're going to need to do problems that do this kind of a thing. Okay, next prompt, find k. Now there's an assumption here you have to make, or it's a property of a probability distribution that you have to remember to figure out what k is. So pause the video, write a little equation, and solve it for k. Okay, you had to remember that all of the probabilities add up to 1. So my equation here, 4k plus 6k plus 6k plus 4k equals 1. So I get 20k equals 1, k equals 1/20. Okay, our next prompt is to create the table with the probabilities. So that table is going to look like this, except you're not going to have all your k stuff in there. You're going to have the actual probabilities for our experiment in these boxes. So pause the video and do that. Okay, so k was 1/20th, so this box was 4k, so that's 4/20ths. This box was 6k, so that's 6/20ths, and so on to fill out the next two. So again, pretty simple stuff mathematically. You just have to understand what you're doing. Okay, so let's pause and take a look at our whole situation. We have a random variable probability distribution. Now we're not relating this to reality at all. The probabilities were given by this algebraic function, and we substituted that in. We knew that it added up to 1, so we solved for k, and that gave us the probabilities. So the probability of 4 being your outcome is 4 out of 20, 5 is 6 out of 20, 6 is 6 out of 20, and 7 is 4 out of 20. We cannot relate this to any kind of a real life situation. This is very abstract, but now we're at the point of having probabilities for our outcomes. Okay, here's a new prompt. For 100 trials, so again, we don't know what this experiment is, we just don't know, but we're going to do it 100 times. For 100 trials, create a table showing the expected number of outcomes. So how many 4s would you get in 100 trials? Remember that the probability of a 4 is 4 out of 20. So pause the video and figure out how many times you would expect to get 4. And the answer is you would expect to get the 4 20 times. And here's how I did that. 100 outcomes, the probability of getting the 4 was 4 out of 20. So I multiplied 100 by 4 over 20 and did some reducing and so on, and I get 20 outcomes. So out of 100 trials, you would expect to get this result, the 4, 20 times. Now go ahead and finish out the table. Okay, so there's really only one other different result, and that was for the two outcomes that had probabilities of 6 out of 20, and you would expect to get those results 30 times each. And then finally, this one is again 4 out of 20, which would be the same as getting a 4. So we have 20 outcomes that would give us the result of the 7. So now there's a quick way to check to make sure that was all done right. All of these have to add up to the number of trials. We did 100 trials, so our expected outcomes need to add up to 100, and indeed 20 plus 30 is 50, plus 20 plus 30 is another 50, so that's 100. So we're good. Okay, here's a prompt. Find the mean outcome for our 100 trials. So our 100 trials were theoretical. We calculated the results. But now we're going to pretend like that actually was an experiment, and we're going to figure out what the mean outcome was. So that's like, remember we had our results were 4, 5, 6, or 7. So what is the mean or the average outcome for that experiment? So what we're going to do is we're going to multiply the results or the number of the result times how many times we got it, and add all those up and then divide by 100. So I'll tease that out a little bit more and explain it. So this is a straightforward average or mean calculation. You just add up all your results and you divide by how many results you have, and that gives you your average or your mean. So we had 24s, we had 35s, 36s, and 27s. So I'm just multiplying my result number by how many times I got it, adding it to the next one, to the next one, to the next one. So this, and then finally dividing it by 100, because that's how many results we have. Now, if you do that math, you end up with 5.5. So that's the mean value of our experiment that we just did. Now, this kind of makes sense. It won't always with a probability distribution, but this one it does, because we have half of our results are 5 and 4, and the other half are 6 and 7. So it makes sense in this case that the mean would be 5.5, halfway between the 5 and the 6. And once we start graphing probability distributions, you're going to see how this makes sense. Okay, so here's our prompt. Calculate the expected outcome for a probability distribution. Now we're going to do that on this distribution we've been working on so far. But before we jump into that, I want to show you the general rule. Okay, so expected value. So that's an E. It's not a probability. It's the expected value of uppercase X. So random variable X. We're not yet into our problem where we're using random variable U. But in the general case, we use X. So the expected value of random variable X is the sum of the little x, that's the value. In our case, that was 4, 5, 6, or 7. So it's the value times the probability of it happening. And then this notation here just means we're going to run that through all of the values of x. So we're going to, basically this says for every little x. So we're going to sum up the probability of each little x times its value and add those all up, and that will give us the overall expected value for a probability distribution. Okay, so now we're putting that last rule into the context of our problem. So check this out. Expected value for random variable u. So we have the number value, that's the 4, that's one of our outcomes, times its probability of showing up. Now remember that that formula has a sum, has the Greek sigma, so we're going to run this calculation through all of our possible outcome values. So 4 times 4 over 20, if you recall from the table, or you scroll back in your notes, the outcome of 5 had a probability of 6 over 20, the outcome of 6 also had a probability of 6 over 20, and then finally 7 had a probability of back down to 4 over 20. So this will give you the expected value of this probability distribution. And remember, this is not a mean, it's not calculated based on experiment. This is looking ahead of time. What is the expected value? So go ahead, crunch those numbers and come right back. Okay, I like doing calculations by hand rather than the calculator. So I just multiplied my fractions or my outcomes by my probability, and I got these 4 fractions, added the tops. I get 110 over 20, which gives us 5.5. So in this case, the expected value did match the mean value because that mean value we got was assuming that we got a perfect distribution. So in this experiment, whatever the probability experiment was that generated the 4 outcomes of 4, 5, 6, or 7, the average outcome is 5.5, which is also the expected value. Let's talk about the difference between expected and mean value. They're very, very similar, okay? An expected value is a theoretical mean, same number here, but this is a theoretical mean for a very large number of trials. So this would be, in theory, if we did 1 million trials, here is the expected value. The actual mean is a mean for an experiment with a certain number of trials. So let's say we do an experiment 50 times and then we record the results. That mean would be for that experiment. Now, as this certain number of trials gets larger and larger and larger, this actual mean is going to get very, very, very close to the theoretical mean. In fact, if you do enough trials, they will be indistinguishable because we know as probability, due to probability, the more and more and more and more trials, the closer your experimental calculation will get to the actual theoretical. So that's the difference between expected and mean. Now think back to that last problem we did. We calculated the expected values for 100 trials. So we get 20 of the 4s and so on and so on and so forth. Now if we did 100 trials, we probably wouldn't get those exact values. So if we did 100 trials and calculated it, then those would be mean values. But if we bump that 100 up to 1,000 or 1,000,000 trials, our numbers would get very, very close to the expected values. One more example. This one involves a dice game. And some students are arranging a dice game to raise money for charity. So they're having people pay money to play the game, and then they win a prize if they do well enough. So here's the prize amounts. They can get $1, $2, $4, $6, or $7. So those are the prize amounts. You pay your money, you play the game, and you're going to win one of these dollar amounts. Okay? Now the thing is that they have to design this game so that it makes a profit because they're trying to raise money for charity. So they have to design a game that makes a profit, but they can't just charge $100 to play a game that could only win you $7. So they have to have a charge that allows people to win some money, but it has to be high enough so that on average, the group that's running the game will net some money, that they'll have a profit from this game. So this is actually a pretty challenging calculation for someone to do who doesn't know what you know about probability distributions. Now, these people met to figure this all out, but they spilled coffee over their notes. So they did have the probabilities of winning $1 and $2, but they lost the 4 and the 6 probabilities. They just don't know what they are. They spilled coffee all over it. They do have the 1/8 chance for getting the $7, but they did remember one key piece of information. They remembered that the expected value was 67 out of 20. So your first prompt is to use the information you have here to find the missing probabilities in those two boxes. So pause the video, think about that. You do have enough information here, especially with the expected value. Okay, the first step is to add up all the probabilities that you already have, because these three subtracted from 1 will be the total of these two. So what I did is I went ahead and added 11 over 40. 1/4 is 10 over 40, so I just made that over 40. And then 1/8 is 5 over 40. That gave me 26 over 40, which reduces down to 13 over 20. Okay, so now we know that these three add up to 13 over 20. So here is a vital trick. I'm going to use the letter K here to designate this probability. Now, the trick here is to express this probability in terms of K. We don't want a new variable because that makes it harder to solve. So we need an expression for here in terms of K. So think about that for a minute and come back. Okay, here's where we use the fact that all of these add up to 1. So if they add up to 1, then these two boxes are going to be 1 minus 13 over 20, which is 7 over 20. Now, if this is K, then this one has to be 7 over 20 minus K. Now, there's nothing complicated about the math that was done, but the critical thinking takes a little bit. So you want to make sure you understand the conniptions that we just went through to fill out this table. We have variables. We can't quite do our answer yet, but we're going to get there. Okay, your next step is to write one equation that you can use to solve for K. Now you're going to have to think about what we know. This is a discrete variable, random probability distribution. So there's things that we can know, and you're going to have to use your equation for your expected value, only this time you have the expected value. And then the art here, the trick here, is to figure out how to articulate all this on the right-hand side so that you can then solve it and find out A, what K is, and then you can use K to figure out the values. Okay, let's see how you did. Here is my plug-in step. So my expected value is going to equal the sum of the probability of each outcome. So, and it's times the value of the outcome. So here's win $1. The probability is 11 over 40. So it's going to be 1 times 11 over 40, 2 times 1/4. I'm making these all over 40 because that's going to help me at the end to reduce. So I have outcome winning $2 times 1/4, 10 over 40. Outcome winning $4, now I just put in my K. I don't know what that is. And then outcome winning $6, 6 times, and then I converted my 7 over 20 minus K to 14 over 40, so I have another over 40 minus K. And then finally, the outcome of winning $7 times its probability expressed in 40ths. So 5 over 40 is the same as 1/8. Now, the rest of this is just calculation. Now you can pull out your calculator and just decimalize the heck out of this and solve it. You could do that. I'm going to keep doing it algebraically on paper. However you do it, pause the video and find the missing value. Find our K. Okay, let's see how you did. Now, lots of steps here. If you see this on an exam, you're going to hope that it's on a calculator portion of the exam rather than a no calculator, because I think it's a lot easier on the calculator. But I like to keep up on my ability to deal with fractions. So check this out. So I ended up with 11 over 40. 2 times 10 is 20 over 40. This becomes just a 4K. 6 times 14 over 40 gives me 84 over 40. 6 times minus K is a minus 6K. And then finally, this becomes 35 over 40. Now I have a bunch of over 40 terms, so I just combine those. I get 150 over 40 minus 2K. So this equation has just gotten quite a bit more simple. I move my 2K over to this side. I move my 67 over 20 on that side, and I reduce my 150 over 40 to 75 over 20. So now we're subtracting 67 over 20 from 75 over 20. That gives us 8 over 20, or 2/5. That's 2K. So 1K is 1/5. Whew, whew, whew. Okay, last step. What is K? So we found out K is 1/5. So the probability of winning $4 is 1/5. Now the probability of winning $6 was 7 out of 20 minus K. So that's 7 out of 20 minus 4 out of 20 gave us 3 out of 20. So that's the probability of winning $6. Now my question to you is, how much should they charge for this game? Actually, let's ask that two ways. What is the break-even charge? In other words, the charge for which they should, over a long period of time, end up not losing and not winning. So what is that charge? And then what do you think they should charge so they can make a profit? Okay, the answer to this question goes all the way back to the beginning of the problem, to one of the givens. We started knowing the expected value, the expected outcome, the expected winning was 67 over 20. So we just manipulate that fraction, turn it into money. So that's $3.35. So if they charge $3.35 over the long term, they're going to break even. They won't win and they won't lose. So that's considered a fair game, like that you could play and the chances are even that you win or that you don't win. I would think maybe charge $4, charge $4.50. That means that you're going to, over time, you're going to win. If the expected value is $3.35, you're going to win because these are higher than the expected value. Okay, let's do an example that relates to a hypothetical real life situation. So we're going to anchor our probability to basically a situation and help a person make a decision based on probability. So here's our situation. Boiled down, we have Scottish newspapers that are sold on Sundays. So I'm a news vendor and I sell all kinds of stuff, and I happen to carry Scottish newspapers because there's some people in my town that like those. So data collected over the years shows the following. So I'm a savvy math guy, even though I sell newspapers. So I looked up all my data and I found out the probabilities of I'm going to sell 2 papers is 0.05, 5%. The probability that I'll sell 3 papers is 0.39%, 4, 0.29, and so on. So these are my discrete random variables. Will I sell 2 papers, 3 papers, 4 papers, or 5, or 6? And here are my probabilities that I will sell that number of papers. Now, if you've already looked at these, you know these add up to 1, so we're good with that. Now, here's my question. How many papers should, the example was with a woman, I said me, but how many papers should she buy or order for next Sunday? Okay? So you might say, oh yeah, it's most likely that she's going to sell 3, so let's order 3 for next Sunday. But the answer might surprise you. So what we want to do is we want to find the expected value, and that's using all of this data in the table. If you're feeling bold, pause the video right now and calculate expected value. Okay, I've set it up for you. I'm still going to leave the calculation to you. So here we go. We multiply the value of the outcome. This is our discrete random variable, selling 2 papers, by its probability, 2 times 0.05. Then you add that to the next outcome times its probability, and so on, all the way through all of our 6 or 5 outcomes in this case. So go ahead, pause the video, crunch those numbers, and come right back. Okay, so what I get is 3.83 papers. Now, obviously, she's not going to sell 0.83 papers. She's going to sell 3 or 4. But based on this value, you might as well buy 4 papers because your expected value is pretty close to 4. So some Sundays you'll sell 3 on average, but you'll sell more often, you'll sell 4. So if you buy 4 papers, you're going to come out ahead. You're going to sell more papers. So that's the answer to that probability distribution question. Now that you've watched the video, take a moment to jot down any remaining questions so you can bring them to our next class. Remember, you can also come back to this video again and watch it for deeper understanding. If you liked or enjoyed the video, please click like or subscribe down below.